So I'm going to present our joint work with Emiliano Lorini on logic for binary classifiers and their explanation. So as for the plan, I'll first give the motivation of coming up with a new logic with two conceptual analysis. And then the second part, we introduce the basic framework of this binary classifier logic, BCL for short. And the third part, some possible future directions. Okay, so as a background knowledge, there's new interest in classifier in the field of XAI, and that approach is called local explanation, which means given a particular input, for instance, we want to know the features that necessarily sufficient for the current classification, or following a counterfactual setting, is necessarily sufficient against the current classification if you're allowed to change the values of that variables. And the Boolean classifier actually by essence can be seen as nothing but a Boolean function. And Boolean function is traditionally studied by propositional logics. So as mentioned, we present a logic for the classifier, Boolean classifier. So why a new model logic? That's a very natural question comes. So we can already give one reason here, because which we do is a slight extension of Boolean classifier in the sense that the output could be more than binary as long as the finite set of values. But also I'll give two conceptual analysis to show it's also quite natural to think classifier from monologic viewpoint. So first is about the standard metaphor of classifier. Well, it is a black box, just as Leopold also mentioned. We have some input S and we put it into the black box and then X as the output. So we claim that there could be a refinement of this metaphor, basically a partition of possible inputs. It means that we can put all the possible inputs, on the table, and then we can have some partition of it formed like a map. We don't know exactly the boundary, but necessarily there's a partition. And this is actually the, say, standard schematic diagram of model logic when we think of grid key semantics. And the second conceptual analysis had to do with Prime Implicant. So as you recall, Prime Implicant is a subset minimal conjunction of literals, which still validates the Boolean function. And we can understand that via model understanding. So that means given an input, and I am allowed to change the values of some variables. And you promise me the classification necessarily holds, as long as I change all the other variables value, but remain some prime implicant staying unchanged, staying the same. And this is of course some modality, because it has to do with necessary versus possible, always versus sometimes. Okay, I hope we already try to convince you this is not very far-fetched to have some model logic for Boolean classifier or Boolean function. So then I will introduce the logic. So we start with the atomic propositions. So in our framework, the atomic proposition or atoms consists of two disjoint union. ATM0 is intended to denote the set of input variables of features, right? And so for the output, we will follow in such a way. So we will first give from a set called decision values X and Y and so on, the intent to denote all the possible outputs of the Boolean function of the classifier. And then we build a special type of atoms, which we call decision atom out of that. So it has to be read as the actual decision takes value X, and let DAC denote all these decision atoms. So this is very special because actually we made every values a single atom, and this is the thing that different with what happens in the features. So this is one thing we add into propositional logic. The other thing we add is a family of operators, this box X5. I will introduce in the next slide what it means. So all we need to know now is P ranges over ATM and X ranges over all subsets of the input variables. Okay, so it should be clear that we have two sorts of X. The lowercase x denote decision values, while the capital X denote a set of input variables. They're not the same thing, of course. Okay, and then I'll introduce the classifier model. It is nothing but a pair, where S intend to denote all the possible inputs, and F is, well, clearly some classifier. And given any input, small s, we can have a pointed model and we can have the satisfaction relation. So it verifies P as an input variable if P is in the set of S. And it verifies a d of x if the classifier gives us x. Negation, but it's not the case. Well, the Boolean cases are as 0. So this is the new thing, of course. So S makes box x phi true if for all the possible inputs S prime, if S and S prime they agree on the valuation of x, then S prime also makes phi true. And this has a catalyst particles rating as phi is necessary of features in X being equal or regardless of the values outside of X. And the other definitions are just defined as 0. So at this stage, it's good to give a figurative example about this. So here we can have a classifier which has 3 arguments. There are 3 input variables. So this point means that P1 is false, not P1, not P2, not P3, and it's a yellow point. So take this point, for example. Which point is this? We have P1, P2, P3 absent. Absent means negation, means false. So it's this point. And of course, it's P1 and P2 and not P3. So let's check the first box sentence. It is true. Why? Because by fixing all 3 variables, we only have this input, and it's a right point. And the second is also box sentence also right. Why? Because by fixing P1 and P2, all we need to concern is this point and point 111, they both red. But the third one is false. Why? By fixing just the first variable, we may have a blue point like this. So I hope it's quite clear that we really give a very simple framework, add not too many things to propositional logic, but can give us better intuition about a classifier. And then we will use this mechanism to represent some existing notions of explanations. Okay, so here is the formal definition of a prime implicant. Recall a literal is an atom, P, or is negation not P. A term is a conjunct of literals, P and not P2, for example. So lambda is a part of lambda prime if it is it is subset part of it. For example, we have lambda as P1 and not P2 and P3. Then P1 and P3 is just a part of the former. And lambda is an implicant of F if lambda validates F, the function. And lambda is a prime implicant if it is a subset minimal implicant of that. And as mentioned before, the new interest on this issue is not finding all the prime implicants of a Boolean function, but to find a prime implicants regarding a particular given input. So thus we have the first notion. It's called abductive explanation or sufficient reason PI explanation, also in literature. So we call lambda abductively explains X at S. If lambda is both true at S, in this view that is local, and then lambda is also prime implicant. And we can see how it works, this representing formula. It is true at S, so it has to make lambda true. And it is an implicant of F if this box sentence holds. So this is exactly what this box sentence does. It means that I'm allowed to change all the possible variables, the values outside of X, out of lambda. But as far as I keep lambda staying its original value, I necessarily still have T of X. But this is not enough for sure because we need it to be prime. And this is done by this red formula. And this diamond part is just the dual of the box X operator. And then following the same definition, we can have the notion of contrastive explanation. So abductive explanation is a minimal part which the classification necessarily holds. And the contrastive explanation is also a minimal part, well, with changing which another classification necessarily holds. And we can define it following the same manner. The third notion is about bias. And then we introduce the notion of protected feature in the meta language level. Protected feature is something like age or gender or color. So we call it decision or classification synonyms. Biased if by only changing some protected feature, we can have a different classification. And this is just our common sense understanding of bias, and we show that it can be formalized in our language. And then I will also introduce some counterfactual conditional, but thanks to Leopold, we are quite familiar with this. So we take the most popular approach, basically closest world semantics of Lewis. We can have a conditional like this. It's read as if phi were the case, other things being equal, then it would be psi. And this sentence can be reduced to our framework by this very long but useful formula. So it is recent in the sense that evaluating that, it consists of two steps. We first find all the closest friend of the current one who make the antecedent true, and then we check whether the consequent holds. Okay, so why introduce this? Because we can put one step further to the current study that if lambda is a CXP of X, then we can have a counterfactual saying if it were the case lambda bar, then it would be the case that not T of X. Lambda bar means we negate all the literals in lambda and conjunct them together. So for example, if I have P1 and not P2, the lambda bar would be not P1 and P2. And the second theorem says a decision is biased if and only if there are some CXP with respect to some protected feature. And hence, we view the contrastive explanation as a special sort of counterfactual explanation, where the antecedent first shall be a conjunction and second shall be a subset minimal conjunction. So let me finish this part with an example, the famous, like the standard one loan example we're quite familiar with now. So let's have a protected feature as being male and living in city, non-protected feature as employed, owning property, and it has two possible outputs to accept or reject the applicant. And let's have a classifier who classifies as only applicants either being employed and owning property or being male and employed can get accepted. So we have a pointed model S that stands for state of Alice. Alice is not a male and is living in city, employed and not owning property. So she fails the two possibilities of getting accepted, therefore rejected. Now, of course, Alice does not know the whole classifier, but following this local explanation, Alice is able to know not being male and not owning property is an AXP and also has two CXP not being male and not owning property. This is of course a bias because there are CXP has to do with protected feature, and also we have a counterfactual if Alice were a male, she would not get rejected. But notice that not here we have a nice correspondence between these two, but they are actually a coincidence. Generally, we don't have.
Xinghan, 2.5 minutes left. So
okay, yeah, fine. So I'll speed a bit up. So we have the axiomatics of our logic. This one already in the Emiliano's previous work, we can show the box empty set is an S5 operator, and it can reduce all the box X to box empty set. And this is something new in our this logic now. We basically formalize a complete function in the deductive theorem, and this one may be the most important one. Inference rules are just as usual. So for technical results, it's sound and complete, and the satisfiability problem is NP complete. Okay, so we can have several extensions, but I think they are not the most relevant to the topic. So I'll just briefly say we can have dynamic extension. We can use it, for example, to model a learning process of a classifier, very simple one by axiomatization. So the key point is that we can use this counterfactual. So it's saying, so first let us have some point. Let's have a new decision value, which means indeterministic, not a particular classification. And it is we have a classifier which everywhere is undeterminate. And then we can have a counterfactual saying if all my closest friends who have some deterministic classification is X, then I just follow those friends. And then I also turn out to be an X point. And this just shows figuratively how it works. And also we have an epistemic extension dealing with uncertainty and about the knowledge of a classifier. We also think of the infinity case. There's a technical difficulty because if we let us ATM0 to be countably infinite, then the set of spaces will be uncountable. So we have to deal with partial functions instead of complete. But there are, mathematical and philosophical reasons supporting this restriction. Okay, so as a conclusion, we have investigated a new model logic, but as you see, really simple. And our final answers to the motivation question, why that is helpful, is that it is both natural. I hope we have some more intuition than the conceptual analysis at the beginning, and also fruitful because of the many extensions. And for further study, well, multi-agent or a family of counterfactuals, And also we can use subsolvers because as we can see, all the framework can be reduced step by step to the propositional operations. Okay, so that's basically what I have. Thank you very much.